Hi guys, welcome to day one of our 100 days of ML series. So today we are tackling the most fundamental problems in machine learning, which is called generalization. We want our models to be smart, not just good at this rote memorization. The core challenge is to finding that sweet spot between a model that's too simple and a model that's too complex. So we call this two extremes like underfitting and overfitting. If you can master this balance, you will build a reliable system that will actually work in the real world. So let's dive into what happens when a model learns too much. So first term is called overfitting. Overfitting is when a model learns from the training data that is so much. For example, it is think of it like a student who memorizes every single practice question without even understanding the underlying concept. So, for example, a student who mucks up everything, not understanding anything. And when this happens, the model starts capturing the noise and the random quirks in the data. So, for example, it is not just taking the model's noise, it will take also random quirks and all the general patterns. And this happens because the model is too complex for the amount of data you have. Like if you have a lot of data, the model is too complex. What model will do? It will just adapt to the patterns and noise and quirks and everything. So it's nothing but it's a memorizing everything. So it's memorizing specific examples like learning in general rules. It's just not doing anything, it's just learning from the rules. And that means it won't generalize well to the new data. So for the training data, it will generalize, but for the real data, it won't. So how do we spot this problem? First of all, we call it accuracy gap. So the accuracy gap is the clearest red flag that you have in when overfitting occurs. So, for example, you'll see a model performing almost perfectly on training data that would be around 99-100% as well. But when you test it on new unseen data, the performance drops significantly. For the test data or the trained data, you see a vast amount of difference, like 99 to straight like 65%. So this is a huge difference between training accuracy and the testing accuracy. It tells you the model is brilliant at memorizing, but it is very terrible at generalizing. So we need these strategies to close this gap. And the first one we'll talk about is like when to stop. So we call it early stopping, which is strategy one. So early stopping is a simple yet very powerful technique to prevent overtraining. So remember, the model starts when overfitting begins. And overfitting begins when it learns all the noises. Okay, so we monitor the model's performance on a separate validation set as it trains. Like so, for example, what we'll do is we'll train the model on validation set as well. When validation error is going down and we keep training, but the model that validation error starts to creep back up, like we stop immediately when we see validation is not improving and testing accuracy is improving, we stop it. So we call it early stopping. So this prevents the model from entering into the dangerous zone where it starts memorizing noise instead of learning patterns. But sometimes we need more direct way to keep the model honest. And if that's the case, we use it. We use a thing called regularization. So that's our strategy too. So regularization is the second key strategy, and it is nothing but penalizing the complexity. All right. So we add a penalty term into model's loss function. So based on the size of its weights, and we have two types of regularization, which is L1 and L2. L1 we call it Lasso, and L2 we call it Ridge. So in L1 regularization, it is great because it can shrink some weights all the way to zero. Okay, so in L1 we can shrink all the way to zero to some of the weights, where for L2 we keep all the weights small but prevents any single feature from becoming too dominant. All right. Both the methods force us to rely on multiple features as well, so it will make more robust and it will be less prone to overfitting. Okay, so these are the two things. Next, we'll move on to the third strategy. We call it cross validation. Now, we have talked about penalizing with regularization, but we know that our evaluation is fair or not. So, how do we keep track of it? Third thing, cross validation is our handy strategy, and it is kind of most robust in comparison with the other two. We call it k-fold cross validation. So that means we split our data into multiple chunks, or we say it folds. Okay, so we train the model multiple times, each time holding out a different fold for testing. This ensures here our model performs. It's not just fluke. Okay, we might be lucky for one or two times, but if we have multiple folds, so with training and testing split both. Okay, so it forces model to prove like it can generalize across all the different subsets in our data, and this gives us much more stable and trustworthy estimate of how our model will perform in the real world. Okay. Next, so this strategy is also good in comparison with strategy 1 and 2. Now, next, see the next strategy. We call it dropout and simplicity. Our fourth strategy brings us to a powerful technique called neural networks, and that is nothing but dropout. Dropout is brilliant trick where we randomly turn off a percentage of neurons during each training step, and think of it like forcing the network to learn from the same concept in multiple ways. Okay, so we drop a particular neurons, okay, and we ask our model to think like we kind of forcing the network to learn the same concept with multiple ways. Okay, but we have to remember sometimes this best strategy is also simple while choosing a simple model as well. So dropout is one. Rather, we can choose a simpler model. If a complex model and a simple model gives the same result, okay, we always choose the simple model because complex should only be added if the data actually demands it. And we have spent a lot of time on overfitting, but now let's think the opposite as well. So what we call it is the underfitting. Okay, we have been focused on models that is trying too hard. But what happens when a model doesn't even learn anything? Okay, which is nothing but underfitting. So that's just the opposite of overfitting. So underfitting happens when our model is too simple to capture all the underlying patterns, and it is like just it is it is learning nothing like. So it is like trying to fix a complex curve into a straight line. You can see here the straight line is there, right? The key difference here is like underfitting model performs poorly everywhere, and the accuracy is very low on the both side, like training and the test data. And how do we fix underfitting? So we have multiple approaches like increasing the complexity, feature engineering. We can reduce the regularization, and we might train it longer. So these are the things. Finally, we make sure like training long enough, or sometimes a model just need few more epochs. And with these fixes, I think we can move very much closer to balancing a model from over and underfitting. So our goal is to generalize. So we call it generalization. The generalization is nothing but we want a model that learns from true signal without memorizing any noise. Okay, so a good model finds the perfect balance between complexity and simplicity. To avoid overfitting, we use techniques like regularization, early stopping, and cross validation. While to underfitting, We increase the complexity, improve features, ensure we train it adequately, and mastering this concepts are crucial because we want to build a reliable machine learning system. So that's a wrap for the day one of our 100 days of machine learning journey. Let's go for the next day, for the day two, and join us the next time as we dive into the next big topic. Thank you, everyone.